Hey everyone, how are we doing? We got Tiffany here. You wanted me to look over the email. Let me take a look at the email. Let's go look at the email. Here we go, Tiffany. And you say, I was wondering if you take a look at this. Okay, let me see here. Do you mind if I comment in like to you right here, Tiffany, about the graphics? Do you mind if I comment right here? Like be like, sure, give me your comments. Hey, Trevor, good to see you here. Let's see here. Tiffany, do you want me to comment just in the chat and just be like, here's my thoughts, Tiffany, in the chat? Does that work, or would you like me to reply email? I'll be like, you can reply here or reply email. Which of those would you like? I can reply via email, or I could tell you my thoughts right here in the chat. Trevor, if you have any questions, let me know. Making sure we're all logged in. That's fine to reply here, right? You're saying reply here is fine. Just reply in here. It's looking pretty good. I'm pulling up the assignment right now. I want to make sure you have the right things for it. Where's your assignment on? We should be able to do pivots tomorrow too. Tomorrow's going to be a big day. Either way, it's fine. Okay, good deal. I'll reply here. So with this assignment, it looks like you have one of the graphics, which I think was your goal to get one of them, right? We need weekly hours worked, gender, and student loans. Let me make sure you have that. Okay, you have weekly hours worked. You have the average. You have student loans, and you have, so I would change the bottom axis where you say student loans. I would change that to gender. So you see you have student loans on the bottom average. Like I would change that to gender because the gender's along the bottom. Average weekly hours worked by male, female, student loans. That is correct. Your title looks correct. Great job on the prepared by. And then make sure to interpret this. So make sure to give the numbers. So change one. Make sure the bottom axis says gender on the bottom. Change 2, write the interpretation, quote the numbers. Does that make sense, Tiffany? You bet. Some Q3, you got it. Just pasting the skeleton. I think it might be. Is it the one with the time series? It might be. Some of them are pretty quick. But you'll want to give a decent write-up quoting the numbers, the people who have the most weekly hours worked versus the people who have the least weekly hours worked, and the differences you see among males and females, the differences you see in whether or not someone has student loans. Try to comment on that, on any associations you might see. And the last part, I don't know if I'll do it, because I kind of did it earlier, but the last one, this is kind of just the thing on visualization number 4 right here, is basically just doing any graphic you want. And here's the thing, this is a big hint for visualization number 4, so let's make this part of the video. No, wrong button. If you look at this right here, you need one categorical variable here, one categorical variable here, and you have one quantitative variable using the mean for that quantitative variable. Down here on the bottom, you're going to, well, that's the bottom one. Up here, it's the same sort of thing. You're doing the average of weekly hours worked, which is the one in the value field, and then you're doing gender and student loans. So here, let's take a screenshot of this. What you actually have right here, if you look at this, is both of these are very similar. I'll take a look at this. You got it, Tiffany. This is a quantitative variable right here. This is the quantitative in the value field, same spot. And then the other ones right here are categorical, 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 categorical. So these visualizations, this is a big hint for the visualization. We'll call this like hints for visualization 4. These visualizations are going to look very kind of similar in the way that they have 2 variables, one in the rows and one in the columns, that are both categorical. And then in the value field, you're going to see a quantitative variable. So you should see, we did one earlier, you should see something that looks like this. And this is kind of how to do the second one, not because you can kind of do this one I did. Don't do the exact one I did. I don't know if someone's going to do the exact one I did now. But make sure to write your own interpretation. But I don't want to do the first one because everyone's kind of doing the same first one, and then everyone can kind of do a different second one. But if you get something like this, you've done it right. If you get something like this right here, you've done it wrong. You can start to see where things are looking a little haywire. Also, this is ridiculous. If you get things like this is ridiculous. This should not be your end products. You want to see something that looks like this right here. This is what your end product is going to look like. Also, if you were to get something that looks like this is an error also. I put a quantitative variable in here, and we are seeing just a lot of craziness. Don't do this. It's quantitative. It almost works, but it doesn't. So these are the errors you're going to have right here, and this is where your visualization is not going to look right, especially if you were to take something like high school GPA, which is quantitative. This is going to get ridiculous now, and it can't even really display. There's just too many values, and if you get things that look like this, you've done something wrong. So if you get a graphic that looks like this, be like, hey, Brian, my graphic looks like this. Probably send me a full view of your screen, and you might have something like this right here. But this is where you've done something wrong. So big hints has probably helped a few people, I hope. You've done something wrong if you have that. What you should be seeing at the end here is you should be seeing something like this for your output. And when you take your screenshot, make sure that your screenshot looks something like the top one, not the bottom one. This right here has everything we want. It has your data table. It has your, let's highlight what you want. In your visualizations, you need your prepared by your name. You need to mention the variable names up here. Make sure it's very clear, like average weekly hours worked. You need to have a y-axis label, an x-axis label. Make sure this corresponds to the x-axis it's on. And you need to have a data table. These are the elements right here. Let's highlight them one by one. The first element you need is going to be your prepared by. Second element you need is a title that mentions the variables. Third is a y-axis. 4 is an x-axis. 5 is down here, a data table, or technically data labels could be above the bars. Not a big fan of the data labels above the bars, but you could have the data labels up there. Down here, you would lose points because you do not need this. You do not need this table because this table right here is the same information being supplied right here. So do not include this screenshot. This is bad. I would take off points here. I'd probably do like minus a point because that's not something we would show in a presentation. So don't show your data like that. Show it like this one up here. Hopefully not with all the highlighting I've done to illustrate what we want on it. But that's got it. That's how to do and get some really great grades on it. Let's go look at Viz 3, and then we're going to do a little 474. So let me take a look. So just make sure to have those interpretations. Look to see if your visualization's good and nice. And let me go over here. Viz 3. I'm congested today. It's so crazy. Today's just, one of those days. People are conservative. Maybe mention Greek before the no and yes. Like you could say people that are conservative for Greek is, for non-Greeks is this, and for Greeks is this. I think this is all right and moderate. You could say Greek, non-Greek. Instead of saying no, yes, maybe say Greek, non-Greek. Like non-Greek is no. And then down here, I wouldn't say proves either. Don't say it proves. You might say at the end, the biggest differences are observed between the conservative and stuff. You might say that the biggest differences I see are between the conservatives, where there is a this gap. This looks like there is an association. I wouldn't say it proves because we don't say proves in statistics. We usually say this is evidence of an association. They have a median. Wait. They have a different. You say medium. They have a different median on the box plots. So the bigger issue on the next one is the box plots. One key difference. So they do have the same median. Double check the value you have for median. You have medium. One key difference is in the box plots are higher than the others. Look at the IQR of the box plots. Outliers should be mentioned too. So look at the outliers. So the visualizations are looking good. I think they cover the correct graphics, but measure the IQRs. And then I would, talk about the similarities between the medians like you did. And then I think you do mentioned the low outlier on the males and the high outlier. But be careful with proven. Talk about like a similarity we see is between the medians, and a difference we see is between the IQRs. With an IQR for this group of this and IQR of this group for this, we see extreme outliers in this box plot where we don't see extreme outliers in this box plot. Does that make sense right there, Tiffany? Great work on all this. Looking good. We're just trying to get to those hundreds. I'm going to click done on the email. But always quote the numbers like you were doing. So you're doing a great job. Looking pretty good right there. Wait. Oh my gosh, that's awesome. Oh my gosh. Oh my gosh, one of my students got a full internship. That's our full position. Well, that's cool. That's got it. Wow. So we have a student who's already got a full internship with Frito-Lay. So if you didn't know it, tonight we have Pepsi swinging by. So we're going to hope that we have a bunch of students coming out, but we already have students getting hired by Pepsi, Frito-Lay. And yeah. Awesome job, Tiffany. Great job. We're going to head over to, what was it? HTT had a question. But Tiffany and everyone swing by tonight. Pepsi's going to be here. We're going to go over to the interview table. We got our interview table right here. I want to like update it, but I don't have time. We got the interview table right here where we'll be doing an interview with Pepsi. Got my computer right here. This is the computer we do everything on. Got Julio Bourbon in the background. Thank you so much, Julio, for swinging by. You get it? Swinging by. Your graphs look good. Graphs looked great. Graphs looked excellent right there. Graphs were the correct graphs. And did you include... You include the... Let me double check again. I want to check one thing because I'm always afraid of checking people off and then making a mistake on what they had. Yes, you have the count and row percentages, correct. And then you have the 5-number summary. Yes, your graphics look excellent, Tiffany. Great job right there. Sounds good. We will just plan to be there 10 minutes early. Perfect. Perfect. I will see you. I will see everyone then. Okay. We are good to go. Pepsi's going to be here. And students are doing a great job. Love it. 474, question 4, making the data frame and don't really know if I'm on the right track. So do you want to do Q3 or Q4? What is your call, Q3 or Q4? What's up, Jacob? Good to see you here. Q3 or Q4, you've got the board HDT, so take control and figure out where you want to go. Which one shall we do? Q3 or Q4, your call. I'm going to get everything situated on the screen for using R. Q3, Q4. Q4 it is. Remember 201, 320, 474. You can ask questions, and your questions will appear in this video. And I promise you, your classmates will be very happy that they get to see a walkthrough of what we're talking about right here. I think we got everything. Q number 4. Here we go on Q4. Let's go take a look at Q4 for 474, homework 2. So here we are with question number 4. Load in the EX3 abalone dataset. Abalones are a weird creature. They're like a sea creature where we get a shelled creature that often we get the meat from as a delicacy. One of which is the rings, which turns out to be a good proxy for age, much like tree rings. Create a data frame called ABSUM that has 2 columns, one named ring and one named average weight. When defining the data frame with data frame, you might refer back to Unit 1 notes on how to do this. So... Yep, let's hear. Let the elements of the rings column of ABSUM be the unique values contained in the rings. So you want to think of this as parts. I don't want to do everything. Use the rep command to define the elements of the average weight column of the ABSUM with all zeros. So we're just going to put zeros in there. The number of zeros needs to be the unique values in rings. So what code can we do? We're going to load in the ABSUM data set. Make sure you have library array class loaded up. What code can we do to find out how many unique values of rings there are? What code can we do? I might do this first part. I don't do the whole thing. What code can we do to find out the unique values of rings? What function can we do to find out what unique values? You might be like, well, that is just a vector 3 through 27. It's not quite. It's not quite. It's not quite. Let's go to the EX3 abalone dataset. Let's go to the rings. Take a look. You might think all those numbers are there, but I don't know. How can we find out the unique values of it? We might do a similar question right here. Let's do this. Let's go to the Survey 10 data frame and let's look at the unique values of desired weight. We could do unique values of weight. Let's do this. This is a very similar question. Once again, I like to do similar but different questions. I don't like to do the exact question, but this is a similar but different question right here. So I'm going to go and make a data frame. First, I'm going to find the unique values of the weights of individuals. So I'm going to go to the unique values of weights. You know what I like to do, though? What do you think I should do to this vector HGT? I don't like the way this looks. This is all the unique values of weights. So what do you think I should do to the unique values of weights? What do you think I should do to the unique values of weight? Because I don't like the way that looks, which is kind of the same thing when I do the abalone data. It's ridiculous right there, the way that looks. What do you think I should do to make it look a good bit better? Because you can kind of tell by the way this one looks. What do you think we should do to the values of weight, just to make it look a little bit more sensible on how we kind of tell someone the unique values of weight? Which these are all the unique values. It means there's at least one person who reported a weight of 95, at least one person who reported a weight of 75, at least one person who reported a weight of 207. So we could find out the unique values of weights, and these are just people. So we could put it in a table. We could do that. How about we go right here? Good answer right there. I like that. 50 points. Good answers. Let's go here and go to sort. And now we have it sorted. So now we've sorted. Does that make sense? Like now we have it as a sorted vector. We could put it in a table, but I'm going to sort it. And now, how about we go right here and we go to, let's store this as X. I just like storing things as something easier to work with. And I go to df, data frame, and I'm going to call it data frame sum. Hint, hint. And if you look at the similarities, and I'm going to go to data frame. Whoops. I don't even know what that one does. Data frame. This is going to be weights. And weights is going to be equal to X because I stored it out there in the global environment. And if you take a look at df sum, what do you notice? It has all the unique values. Now, this is where it gets a little bit confusing because the next part of the code wants us to use a rep. A little laggy here on campus. No! When are they going to get this fixed up? Middle of the day lag. Middle of the day lag. I'm going to call this Y. It doesn't matter what we call it. I just like storing it out here. How about we go through rep, and let's go here, rep 0 for the length of this vector. What did I just create? So you can see the answer of how many I created down here. What did I just create? What did I just create right now? This is a similar but different problem. What did I just create? I'm basically just creating a spot for me to put stuff in. That's like why we're doing this. You might say, well, why did you do this? It's going to be the spot where I store it, kind of like, I could have also repped NA. That'd been perfectly fine also. So NA is just going to create a blank vector of NAs. You're supposed to create a blank vector of zeros. Either one's fine. Just different theory. People might say, you should probably throw NAs in there. Or we could just say, let's just set it to 0 to have a value. That way, if we look back at it and we see it's 0, the value was not changed. Missingness might be better theoretically, though. So we're doing what right here? What are we doing? On line 176, we created Y, which has us repeat NA, which you could repeat 0 if you want for yours. More like you should do that for yours. And then we did it for how many times? This code right here looks like a lot, but it's just the length of how many unique elements there are. All I did was put length around my sorted unique vector, so it returns 120, telling me that there's a total of 120 unique elements. So I'm repping NA 120 times. This code will do the same thing right here. It's just that this code is doing it. Does that make sense right there, HTT? Like if I hard code 120 and I do this for something else, the answer is not 120. But if I were to change data sets right now, it's not going to, the number 120 is not set. It's going to do it for how many elements there are, the length of how many unique elements there are. The sort here actually doesn't matter because we're just looking at the length of it. So it's doing it for how many unique elements there are. It's repeating NA that many times. That's all this does. The rep function, although it looks really complicated right there, just reps like the number 5 2 times. It just repeats whatever it is. So we have this right here where we've repeated it. And now let's go right here and store a second vector. It makes sense, but I'll look at, yeah, it's a little tricky, right? And let's go here to AVG weights. I guess we're doing the same thing, right? Basically. AVG weight equals Y. And if you look at our data frame, always look at what you create. Now you might have zeros, wink, 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 hint, hint, hint. But I've created just a blank spot for it. Does that make sense that I've created a blank spot for it right here where we have all the unique weights and then we have right here we're doing the average weights. Please, whatever you do, do not try to write everything I write and then make little changes. Please notice how many times I run stuff. I make errors while coding. I make errors all the time and my code doesn't work. And the more I write, the more likely it is it won't work. And then the more it doesn't work, the more I have to go back and fix my code and spend time getting it to work. So please go little bits. Go in little bits right here. Get your code working and check it as long as you go. It doesn't take but a second to run this. You run, and then you take a look and you say it worked. Okay, I'm good. You get a 2-second check and you know things are working, so you're good to go. So now the question becomes, we want to take a subset of just people who have a certain weight and find the let's go here to average height. I'm gonna call it average height. We want the average height of people at a certain weight because we already know their weights. So we're getting all the unique weights, and then we're going to get the average height of people at that unique weight. Does that make sense? We're going to go to all the unique weights and get the average heights of all those people. Like we go to people who weigh 120 and we find their average height. We go to people who weigh 130, which is a unique weight. That's what a unique weight is. And then we get all of their heights. So we go to all these people, and then we just get the average for that group. So we obviously want to do a what right here? We obviously want to do a what? Because we're going to say we only want to go to the people who weigh 130. We only want to go to the people who weigh 130, which we could do. We could do that right here. How do we go just to the people who have a weight equal to 130? I'm not there yet, but how could we go to and only talk to those people? We could take a what? How could we go and talk just to the people of a weight of 130? How would we do that? Someone's screaming at who's watching the video right now. 50 points in the chat if you know it. How do we go to just the people who weigh 130? We want to say, I want to only talk to these people. There's a few ways, but there's an easier way. Well, that'll go to position 130. This will be the person in position 130. Close. Give one more guess. I'm going to throw the 50 points out there. All right to take guesses. All right to take a try at it. I like that. So we don't want to go to position 130. We want to take a what of a group. Like we got a whole bunch of people and we only want the people who weigh 130. So think about that. We got a whole big group. We want to say, oh, I only want these people who weigh 130. I only want the people who weigh 130. So I only want the people. Well, we won't want to. Value won't do it. Good guess right there. Another 50 points, Jacob. Not value. Think about this. We only want to take a smaller portion. You're taking from a whole big group. You're taking not quite a sample, but you're taking a what? Think of a function R we have. Not really a sample, but you're taking a what of the big group. You're saying I've got a whole bunch right here and I only want this. Not close. You're so close. Not sample. I'll give it a right here. Not sample, but subset. Not sample, but subset. We want to subset it. So we're going to take a subset of this group right here. And what group are we taking a subset of? We're taking a subset of survey 10. And now we're into the condition part because we're going to subset survey 10. And let's just call it sub. Notice how we run it just to check. That stores the subset. We have no conditions. To get into the conditions part, we put a comma, or that makes a new argument. So here's our comma. We hit enter to make it look nice. And then we say weight equals for logical equals 130. And what do you notice about everyone right here? What do you notice about every single person right here? What do you notice about all the people in this subset? Take a look at the subset and then tell me, be interesting to look at desired weight. What do you notice about every single person in this subset right here? Because we said, go to survey 10 and use the condition. They have the same weight. Great job, Jacob, there. Another 50 points. Only for 130 weight. So now let's go here. And let's go to our subset. And let's go to the height vector. And there's their heights. And let's take the mean. Notice how we keep running our code to check it. Okay, we got the height vector. We're taking the mean of it. And that is the mean height, 5'6", for people who weigh 130. That is the mean height for people who weigh 130. Does that make sense? The mean height for people who weigh 130 is this right here. That is the mean height for people who weigh 130. So now, let's think about this. What's going to change every time we run this code? Every time we run this code, what is going to change right here? What's going to change every time we run this code? Like what value of this code would change? If I want to rerun this for another group, what would change? Not really the seed. The seed controls the randomness. Good guess right there, 50 points. Not really the seed. That controls the randomness. Like I want to rerun it for another group. So what would I change? Like if I wanted to rerun this for another group, what would I change? Like if I'm like, let's do this again, but for a different group. Not quite the survey number, But we're doing this for each what in our data frame. Our data frame is for each what. Do you see it? So there was one of them over here. Each weight. So I should probably change the weight, right? Like I go up here to 170 and I run it, and that's the mean height for people who are 170. Does it make sense now? I can find the mean height for any group, like 150, you name it, I can tell you the mean height for that group. Does that make sense right here? We're changing the value we use. But wait a minute. Don't I already have all these values in my df sum right here? In my df sum, don't I already have all the weights right there? So what if I did the following? If I put df sum here and put the first one, oops, let's put it first. I just did what? Whoa, that's interesting. That's the person who's 75. I am doing what right now? Think about this. This is the third unique weight, which is 97 pounds. And this created a subset of everyone who weighed 97 pounds, which is one person, and then found the mean height. Does it make sense what this code right here is doing right now? This is the mean height for individuals who are in the subset of individuals who weigh 98 pounds, which is one person again. So we're doing basically each person, each group right here, like you're saying, and then when we get to the 100, that'll probably be a bigger subset. So all we're doing is changing this. So do you notice this is the only thing that changes? Can you tell me what you want me to assign that to right now? What would you like me to assign that to? What would you like me to assign that value to right there? Like, because this just keeps changing. Each time I run the code, I just change this to like 5, then I run the code, I change this to 6, and then I run the code again. And it's just printing out the numbers for me. That's awesome. And then I run 7 and I run the code. So what should I assign this to? Because this is what changes. I, yep. And we just use it as a placeholder. You can call it whatever you want. You can call it position, I. It doesn't matter what you call it. Try not to call it something that's already used, but you just give it a name. And I is really short for like the ith position. So now we can go out here and do the following and run the code this way. If you notice, this no longer changes at all, meaning we have just created our what. And this is key right here. You should know at this point, like, okay, I've got it working. I have now created my what, 320. This is good practice right here. So if you're wondering about for loops, my label is 32474 for loop practice. We just created our what. That's evidence right there. It's like, boom, I've got my placeholder in there. I'm probably going to figure out the vector here in a moment. We just created the what part of our for loop. We know for certain we got the variable, we got the vector, we got the skeleton. So what did we create? We just created our what? The skeleton. The skeleton is the code that never changes. And I'm going to add one more thing to it, because whatever value of the mean I get, I want to take that and store that value into the data frame, and I want to store it right here for the average height. So now when I run this, I want you to look at the data frame. Do you see it? It's storing the value. Now, that's interesting. That person is 75 pounds and 75 inches. It's probably wrong data. But take a look. It's updating my data frame each time it runs. It's doing the I+1 for me. It will do that here in a moment. Great question right there, Jacob. Jacob, 50 points. Thank you for asking. We don't have to do the I+1. It's going to do that for me down here in the for loop. I'm kind of showing how it works up here, because now that we have the skeleton, it's going to store into the data frame so we can track the data. We just put the skeleton right there. And we're going to highlight the code, go to code, re-indent lines, and now we're just one step away, or 2 steps rather. What do we need to figure out now? What do we need to figure out now? So what do we need to figure out now? We're so close. So close. We need to figure out 2 more things to get our code to work. Because we were kind of doing it ourselves, but we need to do it. 2 more things. What is one of the 2 things, and what value should it be? We're so close to getting our data frame. It's very similar to the one down there. This is the same theory. Everything here is the same theory. The variable and the vector. What is our variable? The variable is the placeholder for the thing that changes every time the for loop runs. So the variable is the thing you want to change. It's going to go through the vector. Variable equals I. Boom. IU, UI. So there we go. We've got the variable. And now we need the vector it goes through. The vector it goes through is what it becomes each time it runs. Do you remember what I had it starting out as? What did I start my vector at as I was populating this data frame over here? I started my vector on the what position of this? You can see the answers. Almost. If we do vector weights, so if we were to do like, this would have it the first time it runs. We don't want this, but no, good guess. The first time it runs, it's going to put in the values right here. It's going to do all these, and we don't want it to do that. Look over here at how we were running it over here, and you'll see part of the answer of how I was doing it earlier on. And think about, it's going to start at what value, like it's going to store into this. Because remember, when this runs, each time the values are going to be put in for I, it's going to turn I into this, then run the code. So what do we want I to be the first time it runs? The first time it runs, I should be what? Because we're going to store into position 1. Very close, HTT. Very close. But just think about this. What should I be the first time it runs? And I think Jacob got it. I should be 1. Now, actually, you know what? Let's do this. Let's see if it even runs. Cool. So it actually did do it. It actually stored into position 1 up here. And we could view it a little bit better if we just watch what happens by recreating the data frame and then see that this data frame doesn't have anything. And then we run this right here and now look at the data frame. The data frame up here actually has something that confirms it is writing to it. What do you think what do you think I should be the second time it runs? And this is not the same for every for loop. It is for this one though, the way we wrote it. What should I be the second time it runs? Because think about what I should be if it's going to sort of position 2. This is not the same for every for loop. It won't always be this pattern. It should be 2. What do you think I should be the last time it runs? As it keeps going through here and populating this data frame, which you can see down here in this code, as it keeps going through and populating the vector, which you see right here, the df sum average height, as it keeps going through and populating, what do you think it should be the last time it runs? 120. Yep, because it's going to go through and just keep populating that vector there for us. It's going to store the mean into this vector, and you see this code right here. It's going to start filling this out. So we could write 120. That's perfectly fine. Or we could go through here and go for the number of rows in df sum. You say, well, what's the difference? This one's not hard-coded. It still is 120. This right here is 120. So these are the same thing.
It doesn't matter.
It really doesn't matter which one you use, but it kind of does. You want to try not to hard-code something because now the size of the data frame will determine how long it runs. So if someone used a different data frame or had slightly different values, like in the future, it'll run the right amount of times for the length of the data frame. And what do we see? Always look at what you create. And what do you notice? And you do kind of see the pattern that people who generally weigh more have a higher average height. Whoa, look at this. Oh, what did we notice? I saw something dip. Wow. This person is 218 pounds, or this group of 218-pound individuals have an average height of 4'8". That might be some wrong data right there. But yeah, there you go. That is an example. Is it making more sense? Please follow the steps right here. Try to do it along the way, making your subset. HGT, Jacob, how are you doing on this question? We got still open floor for more questions. How are people doing on these questions? Any thoughts? Any stuck or any questions? This is a really good, because you should start to get this populated. And then I think we kind of did everything because it shows the answers. We kind of did the whole thing. Wow, we're almost done with this assignment.
Wow.
We've done a lot. I got some superhero shirts coming in. I'm excited. I've only got like 8 t-shirts. I left a lot of my clothes in Knoxville. And then I've got like winter clothes, but I've only got like 8 t-shirts. And then when I go on Pokemon, I'll wear my like regular t-shirts on Pokemon walks. But then like for class, I'll wear like my better, nicer graphic t-shirts. Like I've got just plain like blue and yellow and green t-shirts. And then I can't wear any green when I do green. Like that's a big thing too, because some people laugh. They're like, how many t-shirts do you have? And I'm like, not a ton, but I can't wear any green when I do this. One of my Rick and Morty says green screen. Send me your code. I'll have to look later. Which class are you in, Jacob? Which class are you in? If you're in 201, you won't be coding. If you're in 201, Jacob, then amazing work. You just did some coding that you don't have to do. Oh yeah, you're in 201. Jacob, 100 points right there. Yeah, this is 474. You just did senior level business analytics. So Jacob, everyone some mega points right there. Jacob, are you 201? Because if so, you just did senior level analytics. You're following along, doing well. You'd be like, hey, maybe I'll do this course. I could take it. I could solve it. If that made sense, you're doing excellent. Yeah, Jacob, are you 201? Yeah, congratulations, Jacob. That's impressive. I'm turning another 50 points. We got time for more questions. If you're doing some tool, yeah, most impressive. Exactly, Jacob. So Jacob, don't worry. Jacob, I'm throwing Jacob 200 points. I've thrown out a lot of points right here. But Jacob, I just want to say I'm proud of you. You hung on in there for a senior level thing, hanging in there, asking those questions. That's just exactly how you learn. And you're like, okay. And you were answering questions correctly. So you're getting it. And so whatever you're studying, whatever you're doing, just remember that. Even if you're not business analytics, be like, if I'm marketing, if I'm supply chain, I just need to be in there asking those questions. So Jacob earning everyone some mega points right there. Doing an example in a senior level course at 201. I love that. One of my students, Colin, who swings by, I need to talk to Colin. Colin, I keep missing your call. I keep missing my call. But Colin came in when he was a freshman. Jacob's like, what chapter is this? This is the chapter we're doing this week? Because this is a lot tougher than I remember class being when we were in class. Where'd the fun go, Brian? No fun. Colin came to class, or Colin came to my office hours and was keeping up with senior level students when he was a freshman. And everyone's like, whoa, what year are you? Are you a junior, senior? And he's like, I'm a freshman. They're like, whoa. So he went on to major in business analytics, I believe. I'm 99% certain. Can we do Canvas content quiz 5? Ooh. We should. That's not due this week, right? Please tell me I didn't put it due this week, because we will not get to that this week. But let's check it out. That's a great question. Let's go look at some Canvas content. That's a really good one, Tiffany. Great work, everybody. I want to say this, Tiffany, thank you so much for working ahead. I'm sure a lot of people are very happy with the questions you asked, because videos get like 500-600 views sometimes. So asking about this, which I'm going to get over to it right now. Asking about this is a great way to help other students. Yes. That's going to have to get moved a little bit, isn't it? Let's do on Monday next week. Yeah, I'm going to have to shift those to like Wednesday, Friday. Chapter 5 is all next week. Chapter 5 is no joke. Here comes some Chapter 5. Due Monday, I'll probably put it to due Tuesday. I'm going to have to make adjustments on this because we lost a day. Why did they give us yesterday off? I tell you what, it was great having yesterday off. It was great relaxing. Let's hop here to Canvas Content Chapter 5. How does the normal probability determine if a distribution is normal? Let's take a look to see if that one's on mine. Yeah, let's go take a look. Here we go. Let's take a look. So the question is, how does a normal probability to plot determine if a distribution is normal? You know what? We're going to use R for this. Okay, I want you to tell me the two things we know about a normal distribution. So I'm going to make some random normal numbers. You don't need to know how to use R. Here's 1,000 random normal numbers. And let's go here to X. And what are the two things you see about, ooh, that's random normal, but wow. What do you notice?
Wow.
That's better. What do you notice about random normal distributions or normal distributions? They look what? They have two characteristics. One being this, that's a word you should know, and the other being the idea of you can kind of, like do like this with them. Go. So what's the two things you should know about the normal distribution? It's got that one peak. Ooh, that's a good looking one right there. That's might be the top one we ever had. So what do you notice about this right here? What do you notice about that? Tell me two words to describe a unimodal symmetric. Jacob right there, 50 points. Now we're back on track with some 201 right here. Jacob, great job. That is unimodal symmetric. Now, when you look at a normal probability plot, so we have to know what a normal probability plot is. Normal probability plots look the following way. Ooh. Now remember, these two are connected right here. Do you see that this graphic right here is just a variation or a way of displaying this data? And the normal probability plot is going to tell us what? The normal probability plot is going to tell us if these data values are what? It's going to tell us the values we observe if they are what? It's going to tell us these values that we see, just like these are just values, like they range from -3 to 3 about. It's going to tell us if these values are what? The normal probability plot, which you see on the screen right here, is going to tell us if these values are normal. Great job, HTT, following along, another 50 points. Keep those points coming. So we're going to see if these values are normal. So it would be kind of, yeah. I don't want to say linear, I say it follows the line. Because here you see, I want to keep this really nice pretty one right here. So here's where it looks like it's normal. And then watch this. Does this distribution here, does that look normal? Does this look normal or not normal? Now, it is unimodal. That's unimodal, but it's definitely what? That's unimodal, but it's definitely what? That is unimodal, but it's definitely what? It's not symmetric. It's not normal because it's not symmetric. It's very, very right skew. Right to the high, left to the low, whatever way that tail goes. Right skew, HTT, another 20 points. You're right, it's very right skew. That is a unimodal right skew distribution. So the thing is when we run the QQ plot for normality now, also known as a QQ plot or normal quantile plot, we see something different. Here is the line if it's normal. I want to highlight this and let you see it even better. This line, which is our good line, the line we want if it's normal, is the yes, it's normal line. Everything you're seeing when it deviates, I'm going to do it in blue pen, these deviations right here are not normal. So when it deviates from the line, which is a linear pattern, then it's not normal. So this is definitely not normal because it came from a very right skew distribution. This one over here is normal because it does what? And remember how we have this red line right here? It's normal because it's following this pattern. It doesn't have to follow it perfectly. If you keep generating data for this, you won't get perfect ones every time. Like all of these come from normal. Even if you see some sort of weirdness there on the bottom, this actually came from a normal. I'm trying to find a really weird one, but all of these are actually coming from normal data. So when you see something that's like, that looks a little weird, like, that looks a little weird. No, it's still normal. Let's see, I want to find a really bad one, or one where I'm like, ooh, that looks a little bit weird. All of these all look pretty, like a little weird. Ooh, look at that. No, that's still normal. All of these are being generated from normal numbers. So the answer to, are these normal? The answer is yes. But let's take a look at ones that are not normal. All of them, so every normal quantile plot right here, or normal probability plot, is going to look extremely weird right here. And what should it do if it's normal? It should kind of closely do what? Not perfectly. It doesn't have to be perfect, but it should do what if it's normal? A normal quantile plot that looks good should do this. A normal quantile plot. Now, people get to say, what's a normal probability plot? A normal probability plot, which you see one here in the background, should do this if it's a good normal distribution. If we have a normal distribution and we plot it with this plot, if it is normal, it should do what? Just explain in your own words. Your own words are going to help you remember this. So it should what? If it is pretty normal, it should do what? If it's pretty normal, it should do what? Mostly, I agree with that right there. It should follow decently. It should be mostly within the red line. Like, nothing's perfectly normal. This one right here is very badly not normal. This is ridiculous. This is not normal at all. And then if we were to look at one that is normal, it should mostly be inside the red lines. It doesn't have to be perfect. You're like, ooh, that's bad right there. Nah, that's just random chance. You're going to see weirdness every once in a while. So the answer to this question is, how does a normal probability plot determine if it's normal? And a normal probability plot is going to have the line is straight. Now you see something about p-value right here. So there's another good talk on this. When it comes to p-values are actually done via the Shapiro-Wilk test for normality, also known as a goodness of fit test. So what is the null assumption, which is what we begin believing for this distribution? We start out believing it's normal. Now, very important. Oh, thank you so much, Vincent. So much appreciate that. Feel free to ask any questions you have. Notice here that the p-value is high. HGT, I bet you know this. When the p-value is low, reject the null. When the p-value is high, just let it what? So remember right here, we have a high p-value and goodness of fit for normality assumes normal, which we can see this in jump output too. I'll do it in jump output here in a moment. But with this right here, you just let it fly. So we assume it's normal. That's pretty normal. Now, I want you to think about this one down here. I'll start some 50 points for Vincent showing up right here. Is the p-value going to be high or low for this one? So think about this one. This one, let's look at it, looks like this. So what do you think? Do you think you're going to reject the null, low p-value, or just let that p-value fly, or let that assumption fly? What are you going to do here to the assumption of this being normal? Reject it, or like reject means like, that's not normal. I reject that. You're crazy to think that's normal. Or let it fly means, yeah, sure, that could be normal. I'll just continue to believe that. I'm cool thinking that. What are you going to do with the idea of this being normal? This is not a p-value, but it'll give insight of what the p-value will be. Because here's what the histogram looked like. And then you're going to reject that this is normal. So that's your histogram. Here's your QQ plot for the same data. And then what do you think the p-value is going to lead you to decide? And this is the p-value right here. Where it says p-value. That's not the one for this test, though. What do you think the p-value be? You're going to reject, which means the p-value is going to be what? When you reject the null, it's because the p-value is what? When the p-values reject the null, when the p-value is high, just let it fly. Let the null fly. Just let it be. Don't reject it. Just let it be. So since you're saying reject the null, the p-value is most definitely going to be what when I run this? And you're going to be right if you say this. The p-value is most definitely going to be what? When the p-values reject the null, when the p-value is high, be careful. Wait, just use the word... You'll see it. No, well, you're close. 20 points. When the p-values reject the null, when the p-value is high, just let it fly. So the p-value here must be very, 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 very what? So very good review and very important for 201. I know we haven't done this yet in 201, but this is like tests 1, 2, and 3. Like this is going to become super important. The p-value here, because you're rejecting the null, must be very what? Low. And low p-values, which you see right here, this is a p-value of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the p-value right there. It's very, very low. So is that statistically significant, yes or no? So remember, statistically significant means it's less than 0.05. So is that less than 0.05? That's all I'm asking. When I say something is statistically significant, we're saying the p-value is less than 0.05. So the question is that less than 0.05 is the same thing as, is that statistically significant? Which means it's unlikely by random chance. So is that statistically significant, HTT? Is it? Yes, very, very, very great job. Great practice right here. And this is a good review. And so what's confusing about this question, and we should notice, is this is goodness of fit stuff. This top part right here would be for a goodness of fit question. How does it determine via the goodness of fit? High p-value would be what we see for goodness of fit, being good goodness of fit for normal, and straight line for the normal probability plot. This is two concepts right here. There's a lot to lecture on with just this question alone. So if you're seeing the answer right here, make sure you understand the theory behind it. I think sometimes people don't go through and hear and understand the theory. Let's do one more version of this, but with jump. Let's look at, so we're just doing one more version of this, covering this. I'll do a new topic here next. Let's go here and look at the distribution of people's GPAs. Woo! Nah, I don't like that because that almost looks good. I don't want it to look good. Let's go here to the how much people spend on their pets. Excellent. Love it. Does that look normal, yes or no? And this is if you can follow along with this and answer these questions, you understand what's going on right here. Does that look normal, yes or no? This is way number one, which is look at the histogram. Does that look normal, yes or no? So we can look at the histogram and be like, is it unimodal symmetric? Yes or no? Is that unimodal symmetric? We can even change the bins a little bit because bins are subjective. What do you think? Does that look normal? Yes or no? And normal data is important for all classes. 320, 474. What's up, Trevor? Good to see you. Definitely not normal. Definitely not normal. 20 points random, Trevor, appearing right here. So that's definitely not normal. So how should the normal probability plot look when you go here and you go to normal quantile plot, which is a plot that shows us if it's normal? How should it look? Should it follow the straight line or not follow the straight line? So should it follow a straight line or not follow? There we go. So should it be a straight line or not follow a straight line? So the normal quantile plot is going to be the graph we saw second. Should it follow the straight line or not follow the straight line? This is a normal probability plot. So remember, you just said it's not normal. So when we test it with the normal quantile plot, also known as the normal probability plot, should it follow the straight line or not follow? It'll follow if normal, so then it won't follow. We can circle back, Trevor. You bet. We did that in the morning video. We could circle back and do it again here in a bit. You got it, Trevor. It's at the end of the morning video if we don't have time today, but it's in the end of the morning video. So it's going to not follow because it's not normal. And look at this. Oh my gosh, this is ridiculous. So now it doesn't follow the normal probability plot because it's not normal. Does that make sense why this one does not follow it? Because it's not normal. It's very skewed. So it does not follow that red line there. Now, when we do a goodness of fit test, will the p-value be high or low? this is review now, good practice. When I fit a normal curve to this, is the normal curve a good fit, high p-value, or low p-value, bad fit? And we haven't seen the answer yet. When I fit the normal curve to this, is it going to tell me that it's a good fit or a bad fit, low or high p-value? So what do you think it's going to do? Low or high p-value, good fit or bad fit? When I fit the normal curve to this, it's going to do a low or high p-value when I fit it. So I can go right here and go to goodness of fit test. What do you think it'll do? I have top chat. I need live chat. I hate that it does that. It's going to be a bad fit. Exactly. It's a bad fit. So remember, we assume it's normal, so we're going to reject that. So since we reject the null, the p-value is going to be very low. And it does 2 tests, actually. It's going to be low. Good. Jacob, don't worry. Good practice right here. Jacob, 50 points, taking a stab at it. Don't worry. It's a low p-value because, remember, the normal curve is a bad fit here. If the p-value was high, you would believe the null. And you'd be like, well, I believe that it's normal. I continue to believe that what we observed here is likely given the data is normal. So the p-value being low here means what we observe is unlikely given the data is normal. So I reject that the data is normal. So we have strong evidence. Those are both p-values right there. We have strong evidence to reject normality. Do remember, and we'll talk about this more in class, that the assumption for the test, which this is the same sort of test, the assumption for the test is that it's normal. So when you see a low p-value, you reject normality. But if you see up here a high p-value, that means you do not reject normality. So notice how this looks really good, and it came from a histogram that looked like this. So in this instance, the p-value was high because the histogram looks good, and the normal quantile plot looks good, so it's very likely it's from the normal distribution. In this example down here, the p-value is very low because the normal quantile plot looks very bad, and the histogram looks very skewed. Does that make sense when you see it? Hopefully, this is a concept where people lose a lot of points and usually just guess on the test, and I feel so bad. You just have to be like, what does a normal quantile probability plot do? Normal probability plot is a plot that shows us the probability of it being normal. When it follows the red line, it's more normal. Here's where it follows and it's more normal. When it doesn't follow, it's less normal. What does the goodness of fit test do? It tests to see if the distribution is normal. So this one right here, what would you conclude from this goodness of fit test? Continue to believe that the data comes from a normal, or reject that the data comes from the normal? Option 1, continue to believe it comes from the normal, or reject that the data comes from the normal. Because we assume it comes from the normal to begin with, which is weird to think, but we do that. So would you continue to believe it comes from the normal, fail to reject the null? Or would you reject the null and say, I have evidence it doesn't come from the normal, with that p-value over there? So that's a high p-value. When the p-value is low, reject the null. When the p-value is high, let it fly. So what would you do? Throw some 20 points, let people think that one over. This is a good review. This is a tougher topic. Pretty much stay normal. Yeah, it's, the idea of like you would continue to believe it's normal. You don't have evidence to go against that. So you would say, I still believe it's normal. I do not reject that it's normal. I continue to believe that it's normal. Exactly. And then for this one over here, you'll notice the p-values are low. So you're going to reject that they're normal, and you've got a lot of evidence. Like the histogram doesn't look normal. It's not unimodal symmetric. We fit this green one over top of it, and you can tell the normal probability plot doesn't look straight right there. So that's great. That's a really good section on that one. Here we're going to do a cut. So that whole entire section right there was just on normal probability plots and goodness of fit tests. What is 0.05? Jacob, great question right there. 0.05, and hopefully, so p-value less than technically alpha, but alpha is usually set to equal 0.05. Jacob, those are the top tier questions we want, because you might be like, well, what is a low p-value? P-values below 0.05 are considered statistically significant because alpha is the point at which something's statistically significant, and we usually assume alpha is 0.05 unless stated otherwise. That's going to be super important for later in the class. So when someone says, well, wait, what is low? You can be like, p-value below 0.05 unless otherwise stated, where someone says, use a different level. Does that make sense right here? So if I were to show you, let me show you real quick results right here. You ready? I'm going to show you results from a test. Here we go. Okay, random test on the screen. I want you to tell me, are these results statistically significant or not? Can you do the question? Yeah, we'll do one next here. You got it. So I want you to tell me if these results are or are not statistically significant down here. Are these results right here statistically significant? You bet, Tiffany. We'll do it next. You got it. Are these results right here statistically significant? And that's a p-value. That's because it's prob. So is that result right there statistically significant? Using an alpha of 0.05, is that result statistically significant? Who knows? Is that... It is significant. It is statistically significant. And why HTT? If you want to explain to them why it's statistically significant, you just look at it. And we were literally covering this in 320 today. If you look to see if something is statistically significant, you just look and say, is it less than 0.05? That p-value right there is less than 0.05, thus it is statistically significant, unless someone states another alpha, like at the 0.01 level. But 0.05 is used throughout pretty much all disciplines as the general level you start off with. Below 0.05, that's it. You say, is that less than 0.05? It's a p-value. It's less than 0.05. It's statistically significant. This one right here is not statistically significant for what we're investigating, which means we don't have evidence. What we saw here is likely given the null is true. So that right there is not statistically significant. These ones below it, since they are p-values also, are statistically significant because the p-values are below 0.05. So yeah, that's got it. We're going to do Tiffany's question next right here. Great job, Tiffany. Working ahead. Excellent work. Let's go take a look at the next question. Was it a runner question? Miss here, could you do the finishing times, local 5K? Yep, got it right here. Here we go. Let's hop over and do another Canvas content question. Let's go check it out. The finishing times of a local 5K 3.1 mile race, 3.12. Terry, what are you doing right there? We gotta go check this out. 5 kilometers to 5 kilometers to miles. 3.12, right? 3.106. Oh, I was wrong. I thought it was 3.12. There's that little change on there. Yeah, it's a little extra second or two on your race. Just saying. Okay, the finishing times are normally distributed. Means a unimodal bell-shaped curve, unimodal symmetric, with a mean of 25 and a standard deviation of 3. Now, here's where you really want to get some practice. You want to be able to draw this out. So when you ever hear something is normally distributed, you're going to draw the Gaussian curve. Gauss. He's Deutsch. He's Dutch. That's the Gaussian curve right here, the unimodal. Take a look how it's unimodal, one mode, and it's symmetric. That is the unimodal. Got the unimode right here, and symmetric nature of it right there. Unimodal symmetric curve. Now, the way we usually abbreviate this when writing it out is a capital N right here for normally distributed, and then we put the first value, which is the mean, and the second value, which is the standard deviation. So then we plot in the middle right here the mean, because that's the center of the curve. It's also the median, but we don't use the median because it's normally distributed. And then we go up 1, a 2, a 3 standard deviations. And we go down a 1, a 2, a 3 standard deviations. And you're really going to see that here where each time I increase this, I increase it by a value of 3. So I'm going to go up here to 28 and do the same thing by increasing by a value of 3. We go here to 31, we go here to 34, and then we go down by a value of 3. Same sort of idea. It's just each time we do this, we're just, it's going to grab my 28. Why you do that? We go down by a value of 3, and hopefully I don't make any errors. But we're just going down by a value of 3 now. Each time I go up or down, I'm doing it by a standard deviation. One thing I like to do, and I always suggest, is drawing what is called the standard normal curve. The standard normal curve has z-scores on it, which tells you how many standard deviations you are above or below. So if I were to tell you, it's interesting, 5K times. If I were to tell you, and put this in the chat, my running time had a z-score of 1, then what would my running time be? For this 5K, I'd feel sad about that. Trying to get in shape to run a 5K, and if I told you I had a z-score of 1, what would my time be? If I had a z-score of 1, what would my time be? So these are z-scores down below, and the other ones I like to call the context. If I had a z-score of 1, that's the mean. Standard deviation is the distances these are apart. If I had a z-score of 1, I'm 1 standard deviation above the mean. Great job right there, Tiffany. Good guess. If I am 1 standard deviation above the mean, I had a time of 28. Does that make sense? If I have a z-score of 1, I am 1 standard deviation above the mean. Now, here's a harder question. Someone has a z-score of 1.66666. What was their time in the race? I could write it on the screen. These are good questions. These are test questions. someone make it bigger. Someone has a z-score of 1.66666. What was their time in the race? So you can kind of see the answer down here. You should have a good guess of it. But if that is their z-score, then that's how many standard deviations they are above the mean. You are correct. Great job, Tiffany, right there. Because you can actually go and just times that by the standard deviation. Because think about that. That's how many standard deviations they are above the mean. They're 1.66. Kayla, good to see you here. Excellent work. Kayla, I showed your app and the class was just like, what? And I want to show you, Kayla, if you have 6-7 minutes to hang out, I want to show you an app I created in 2 hours. I'm proud of myself. I'm proud of Brian. I created an app in 2 hours over this weekend to do some fantasy football drafting, and I'll show it to you here in a second. 2 hours. I was very excited. I was like, yes. I used a lot of the shiny widget apps. They're really great. And so let's take a look at our question right here. Our question says, what percent of runners should be below 22 minutes? 22 minutes has a z-score of what? Oh, thank you, Kayla. 22 minutes has a z-score of what? What do you notice about the z-score of 22 minutes? What do you notice about the z-score of 22 minutes? We've drawn this out. This is an amazing test question. There's ones like it on the test. What do you notice about the z-score of 22 minutes? The z-score of 22 minutes is what? Yours is 31. Make sure to draw it out. So draw out your distribution right here. Yours might be different. I'm going to do this one right here. So yours might be 31 or 21, and I'll give you some hints for yours. But I'll have you see which one you get. So what do you notice about the z-score for 22 minutes? It's at -1. So we're going to draw this right here. Now here's where we use the empirical rule. The empirical rule states between here and here, I was using the eraser still. The empirical rule states between -1 and +1 is 68% of the data. Between -2 and +2, which maybe you're more outside of, is 95% of the data. And between -3 and +3 is 99.7% of the data. So if 68% is in here, what is total outside of here? So I'm asking about, let me be very specific. I'm asking about these green arrows I just drew on here. For those green arrows I just drew on here, what percent of data is outside of there? If 68% is inside, what percent is outside? If 68% is inside, what percent total is outside? So if 68% is in my hands, then think about what would be outside. Like this is 68% inside of here. So what is total outside of it? 32. And then this is symmetric right here. So this is 16. So that's 16 up there and 16 down here. This one might relate more to yours. Now be careful. If 95% is inside, what is total outside? If 95% is inside this, what's total outside? Like this right here is 95% of the data. So then what is the remainder outside here? Like the green portions I've shaded is the not 95%. And then we're going to cut that in half because there's two of them. So we're like, okay, 95% inside. So outside is remainder of what percent? And then there's just cut it in half because they're both equal portions. So what would that be right there? There's 95% inside. Boom, Tiffany, that's some 50 points right there. That's top tier answers. Yep. You're doing it perfectly. And you'll probably see the next one. And this is a great graphic that we're doing right here because we're labeling everything. And then the last one is that there's 99.7% inside. So that leaves only 0.3 outside because that's the remainder. It's a very, very tiny percent. It's 0.3 of this curve, a very, very little percent. And then that means what? It's going to be very hard for me to write this with my horrible handwriting. You cut 0.3 in half, and you get 0.15. And here's where you want to be careful. Because this question right here asks, what percent of runners finish below 22 minutes? So I'm going to go right here and shade in, and I'm going to go below 22 minutes. And the answer should be pretty obvious. Exactly, Tiffany. Excellent work. Yep. And do you see the answer to my question? And I'll answer yours. Thank you, Tiffany, for following along. I'll kind of answer your question, or I'll help you find the answer. Since mine says below 22, what's the answer to my question? Oh, and I did my 16 a little bit weird. Let me... That should be right there. 16%. And then what does yours say, Tiffany? Does yours want above, below, or what? So you always be very careful, plot it and show it and be like, what does that look like? Does yours say above 28 or you said above 31? So what way am I going to shade to go above 31 right here? Left or right? So I think yours says above 31. Make sure it has the same like mean standard deviation too. You are correct. Great job, Tiffany. Yeah, that's exactly, not saying you got it right, but does that look like, and if you shade it, this is where you know you've done it correctly. Does that make sense, Tiffany, how we're working this? Question 3, I think, did we do? Yeah, we take a look. We just did 4 earlier. I think, and we could do some 3. We did 4 early at the start of the video, so check it out. We were doing the EX4 abalone, and we did it with like height. We did it with a different data set, so check that out. We can do some question 3. I don't think we've done that one completely yet. But yes, so make sure to draw this out. Make sure to understand the notation that when we draw something right here with the normally distributed with a mean and a standard deviation, the value of the standard deviation right here is the value of the separation between these values. So that is how much we go up and down each time for the standard deviation. And then the value of the mean, which is mu right there, is the center. This right here is a really good review right here, shows what you need to know, and we can figure out the answer to our question just depending on what it is. But yeah, the chocolate chip company manufacturers will come back, and we'll do that here in a second. You got it, Tiffany. We'll come back. Remember, draw it out, and here I'm going to drop you a hint. You might, if it's not using the empirical rule, we'll be looking at this question section here in a moment. But check out the David Emily applet. We'll be checking that out in a moment here. You got it. We're going to do Muhammad's question, and then we're going to come back here and do the question. But thank you, Tiffany. Amazing questions today. And so Mubot's putting in the chat our applet that we use to help out. So good stuff right there. Let's go check out number 3, false 74. Here we go. What does number 3 say? Number 3 is... let's take a look. Dirty. You ever just slowly lose your mind? Perfect. Let's go check out number 3 for 474. Here we go. Let's just jump into it. So let the time series have the elements. We're doing certain elements here to start. First element, 12.8. Second element, 3.5. Third element, 4.4. My average is NA instead of 0. Put it as 0. We'll check it out. Message me. I've got a lot of Discord messages. You know, it populates pretty quickly. Message me and I'll take a look. Sometimes it might take me till a little later because we're doing the Pepsi thing tonight. But the time series has these elements. Okay, cool. So we have a time series vector with these elements. I'm not going to do this full thing right here. And we get a check right here, which is so nice. We love sanity checks unless they're insanity checks. And then we have right here the time series evolves via the following equation. Starting with the 5th element. Okay, so I'm not going to do everything right here, but I'm going to identify key parts of this question. What does it look like we have right here? Let's actually do something really nice. Let's go to the editor. It's going to take a moment. Let's identify the parts of this question, and then let's just take a look, because this question kind of gives it to you, but you just have to know the parts. So with this, there it goes. We're in the Markdown editor, which is a really nice feature, and you can always skip to questions. Sometimes I forget that even, to see what's showing right here. What is this? This code right here is the what. And we can actually just bold this and be like, aha, we have found the what. What have we found right here? This code right here has placeholders in it. It looks like it can just repeat every time we run something. This code right here looks to be the what. I think we found something. It's the skeleton. That looks like the skeleton to me. So that right there is the skeleton. Pretty certain about that. And then down here it says, starting with the 5th element, evolve this series so it has a total. Great job right there, Mohammed. Yep, everybody gets some 50 points right there. Start with the 5th element and then has a total of 200 elements going through all of them right here. So we're going to start with the 5th element right here. It's going to become 5 at first. And then we're going to go through 200 elements. So maybe, what do you think's going on right there? We're going to start the 5th, go to the 200th. So any ideas of what we have right here? We're going to start at the 5th and go to the 200th. So what do you think we should do? We're going to start at the 5th and go to the 200th. What do you think we should do? We're going to start at the 5th and go to the 200th. Maybe that sounds like the what we're going to do. We're going to start at the 5th and go to the 200th. Let's kind of like go here. And that seems like a pretty important portion right there. I don't want to quite say what it is. You figure it out. But that sounds like maybe that's the something something. Maybe this is, some vector goes through. But that sounds to me like something we're going to use that is going to be assigned to the value of t. Wait a minute. We have the value of t right here. So the value of t, we can't highlight it. That's unfortunate. The value of t also seems important to me too. T seems to be a placeholder. Now you could use I, but you'd have to change some stuff here. You can use I. You can use anything you want. I think you're on the right track, HTT. I think you're getting it. So I don't want to quite say, don't put the following as or anything. But when you make this and you type FOR, you're going to get the container, and in here goes the skeleton, and then you got the variable you're going to use that's going to change. That's whatever the placeholder is. And then you got the vector it goes through. And so then you have the skeleton, the code that repeats, that is going to just have replaced in it, or the variable in the code is going to be replaced by the vector elements as you redo the code every time. And it's going to do all that for you. And then you just have to run the head of it to check. But is that making sense right there? It's like hard to not do this one, but theoretically, everything right here is explained, at least going through, like we have our skeleton, we have our placeholder, we have our vector values. And so by doing this, we can then create the code down here. And yeah, I try to leave these codes off that I don't actually do them. And remember, don't just copy everything I write down. Try to like follow along and be like, because I try to like hint at everything. Enough hints. How are you doing, HGT Mohammed? Are you getting it? Like, are you wondering about what the variable is, what the vector is, what the skeleton is? Because the code kind of, this one lists it out a little bit. I think is that the full thing right here? Let's update the forecast equation so that it has a trend is added on the series. On average, each sequence is increased by this. Starting with the 5th element. Yeah, so then you're just updating it. So then what do we see right here? A change to the what? What's going on? 30 minutes. What is this a change to with this code? We have changed the what? You're good? Yeah, this one, once you see it, you're like, oh, man. I've worked questions like this in office hours, and then I show it, and someone's like, is that it? And I'm like, yeah. And they're like, how did I not see that? And I'm like, just once you do a bunch of them, you're like, oh, I see it. It just takes practice. We keep saying that. You're not going to learn these things overnight. Anyone who becomes a coder overnight is a genius, and I wish I was a genius. Oh, yes. Let's do it. You got it, Kayla. I totally forgot you were here. Let's go look at the draft builder. You got it. Here we go with my draft builder 9000. Let's go take a look at it. Here we go. So this is the code. Oh, that's not the right one. This is the code right here. So this is the code I wrote to do my fantasy draft right here. I was really excited. Everyone's using all those. I didn't use Font Awesome. I think Snea's the one who got the Font Awesome working for us. We were looking at that because I'm really excited to see all the apps people have been building. But what this does is this lets you see the rankings, and we've got over here the control panels. I just don't use dashboard layouts. I should have used a dashboard layout like a control panel over here like you did. Probably would have made it look a lot better if I used a dashboard layout. I showed it to my dad, and he was like, I'm really impressed, son, and that just made me really proud. But you can change the way people are valued on this. It's just equations going on in the background. So you can make it so like tight ends are super valued. You can downweight your running backs, and now you see quarterbacks. But I was going to make it, yeah, I know, right? I was going to make these more reactive so that they would change the values. Like I need to do like an update slider or whatever, that it would change the values based on like you can upweight your quarterbacks. But all the equations, thank you so much, yeah. And then you can go right here and do, I love the search fixtures. Like you can find Gronkowski right here. We don't even want to name that name. But you could find Gronk. You could see right now his current rank and all that stuff. And you just go through and update it. But yeah, as you go through here, the one bummer is it needs one person selected out of each group to do subsetting for some reason. You could remove quarterbacks. You could remove wide receivers. You see right now, like running backs are very highly valued with the new equations. Oh, value. Wow. What happened to the running back values? What? That's weird. I wonder if the app's working properly. It's working properly in this state. I should bug test it more, but it's doing all the calculations over here in the background by like how many people are in each group. I think I have an error somewhere. I think I have a small equation error, like with my copy pasting. I needed to look through here and make sure I changed like wide receiver, tight end, because I think I have an error. Like something, the top player in each group is coming back a little bit weird. So I think my subsetting, let me look at my subsetting real quick, and I'm going to go back. There's like, it's all copy paste. Does the info update as the football data changes? No, it's just for the one draft. It's just when you do your one draft right here. There's my data tables on those pages. Defense, tight end, wide receiver, running back. So are the subsets being done properly? Wide receiver, tight end, running back, DST, defense, QB. Something a little weird is happening. I need to trace back the error, but it worked pretty well. And those are all just the sliders. I wish, yeah, you have to go in. So when you're doing it, I think you're asking about like, so the numbers change like as you select players, like when you go to rankings, like if you see right here, they currently have, Patrick Mahomes currently has, these both guys have this rating right here of 10.593. So when someone selects like Patrick Mahomes, which happens really quickly, you're going to see this guy up here get valued more. And you see now Christian McCaffrey or Dalvin Cook, like Cook can be selected also, and it'll update Dalvin Cooks and their ranks. So it should be changing it. Hopefully everything's changing. But the point is that it updates the scores and updates the points, and you get like a new point total. I think it's updating. It should be. Yeah. But yeah, you just go through here and select players, and then you should see updates on scores. Yeah. Should be working. Maybe I didn't do it perfectly. We'll find out. We'll find out if I win or lose. But I had a lot of fun making this, and it does, as far as I know, update a bit. Like, here we'll go. So we should see Waller update. If I select Kittle, then they currently have 11.74. And you see now he's worth way more. So because we're running lower on tight ends, this guy's worth a lot more now because his value went up when Kittle was selected. So the list updates and moves people up or down. Yeah, exactly. And then searching and splitting columns, you can just search by positions and stuff like that. So you can go by ranks or points, and this is just the raw points, and then the values over here are going to be different. Because right now, apparently, QBs, there's not actually that many great QBs. So Josh Allen actually had a very high value. I think I took him a little bit early in our second draft. And then I got Brady also. So I was like, well, crap, I'll scoop up Brady. But Brady, I think, is being undervalued this year. You never know. Brady, he's just going to have that 1 year where he has a bad year and eventually they start someone else. But maybe he's got that contract with them. Like, no matter how bad his year is, they'll let him finish out the year. If I was Brady, I would tell them that. I'd be like, no matter how bad my year is, I want to finish out my year. And that's my contract for being Brady. Because you know he loves playing. That's Brady right there. Look at the chocolate company. So Kayla, thanks for hanging out. Check that out. Yeah, it's all the practice, and I've gotten more practice. I've gotten better at making these things. You've definitely pushed my skills by showing what can be done, and the shiny widgets helped because I was using that selection thing. I didn't know about the selection thing until I started looking into shiny widgets. And now we have shiny widgets. Let's go check out another question right here. Yeah, thank you. I just like building stuff. Like, how useful was that? I don't know. For my family draft, it was more useful because we don't use ESPN. We do it over the phone. So I wanted a better way to track it than just like crossing people off a list. I want to see how many players are available. I could have had it tell me that, like, there are this many running backs available with like a rating above blank. So I could have had it report to me anything. It would just report like, we're running low on good running backs. There's still a lot of good running backs. So, at some point the running backs aren't worth that much. So it's like, why pick more running backs? But you never know. It could be someone who's way undervalued. That's where your sports knowledge comes in, and that's the sport knowledge I don't have. I just do the stats stuff. Let's go look at that chocolate company thing right here. We'll end off with the chocolate company question. What's the point of building if you don't enjoy? Yes, exactly. Like, to me, like, how good is the app? I mean, I think it's good, but is it going to help me win instantaneous? No. You got to have that sports knowledge. You got to have that sports knowledge. Bye, everybody. Thank you so much for swinging by. We got here 50 points for a random Kayla appearance. Let's head over here and start taking a look at some data. 201, we got your Canvas content question. The Chocolate A Boom Candy Company manufactures many types of different candies. The most popular Valentine's Day box of candies follows a normal distribution of 473 grams and a standard deviation of this. Now, Tiffany, what are we going to do once we see this right here? If we see a normal distribution with a mean and standard deviation, what's the first thing you think Brian's going to do? You decide to buy a candy box and weigh it. The box of candy weighs 458. Calculate the z-score. So what's the first thing you usually see Brian do when you see a mean and standard deviation? You don't have to do this for every problem. Yours is different numbers. Don't worry. We're going to do this one. I'm going to have you figure out yours. I'm going to have you figure it out. You got this. This one's not so bad. We got this. So you don't have to do this for every problem, but I highly suggest it. Whenever you see a mean and standard deviation, here's what I suggest doing. I suggest going and drawing your normal curve. To draw the normal curve, make a graph. Yep. And that's the number one thing to do to like double check answers. Especially when it comes to the test. If you're running short on time, you don't have to make a graph. Now we're going to go and we're going to put the mean and standard deviation in there. Great job, Tiffany. Great job. Let's go put our mean and standard deviation. 473, 19.6. Oh my gosh. That stands for the mean of 473 and the standard deviation of 19.6. Now, this is what you would do if you're doing a test. I hate decimals. We've got our friend David M. Lane right here to help us out because I hate decimals, and I'm going to make this look a lot better really quickly. If you're working a problem like this on homework, I do suggest drawing it out to practice. You're just going to go up here 19.6 each time. Mubot's going to tell us about David M. Lane right here, which is going to really help us out. We use this for a lot of the assignments. And this right here, we can go and we can put in 473 and 19.6. And there you go. There's the drawing. I hate that it doesn't do the third standard deviation sometimes, but here is our curve. Now, we've just drawn this out nice and perfectly, except for that last number. We're just going to take a screenshot of it and bring it back over here to our Word document where we have the same drawing. It didn't give us the last number. I don't know why David M. Lane's applet doesn't do that, but we have here the drawing for us because maybe my head goes there. The question is asking, it says, what is the z-score? We'll talk about what a z-score is here. It says, what is the z-score for a weight of 458? So z-scores are how many standard deviations something is above or below the mean. And we don't see the third standard deviation because reasons. And it was 4, it's very important what the number is. It's 458. This gives us a decent idea. If you had to guess the z-score, Tiffany, what would you guess? I just want you to take a second here and just guess it. Because the z-score is how many standard deviations something is above or below the mean. You might say it's a little bit less than what? So if you were to guess the z-score here, just take a guess. It doesn't have to be super close. Just take a guess. You'd be like, it looks about this. Because we'd say, where is 458 on this graphic? It's about here. 458 is about there. I can't draw. So if you had to guess the z-score, what would you guess? So how many standard deviations is this below the mean right here? Because we're looking at this. We're saying how many standard deviations is that below the mean? It looks a little bit less than what? Great answer right there, Tiffany. Yep, and that's a good guess because now you can check your work. And here's how we're going to check our work. The formula for a z-score, and this is where it gets a little bit easier. And this is a normally distributed curve with a mean of 473 and a standard deviation of 19.6. And so now we do observation minus mean over standard deviation. That's observation minus mean over standard deviation, which is we observe 458. We subtract from it 473 because that's the mean right there. And then we divide by 19.6. And we know the answer should be close to like negative 0.9. We know it should be close to that. So now we just solve observation minus mean, it's below the mean, which means it's a negative z-score, divide by 19.6. And we weren't super close. Maybe my drawing's a little bit bad. It's probably closer to about here. So that would be a little bit more obvious where it's at. But it's a decent enough guess. It actually rounds to negative 0.8, but this is negative 0.76, which means that this observation right here is 0.76 standard deviations below the mean, or 0.766 or 0.77. So negative 0.77 when you round it to 2 decimals. Does that make sense there, Tiffany, on how to do this one? A z-score, oh, I put a bar right there. That should not be bar. Y is observation, Y bar is sample mean. So observation minus mean over standard deviation equals z-score. And always try to draw it out for practice. The more practice you have looking at this and understanding where it comes from, the better you'll do. And the z-score right here turned out to be negative 0.77, which means this box of candy right here is 0.77 standard deviations below the mean. Tiffany, excellent work. It's the end of office hours. Got to start teaching here in 18 minutes. 18 minutes. With that, we'll be back, everyone. Today, tomorrow, swing by Tiffany if you want to talk to PepsiCo and say hey to them. We'll be back tonight with some more business analytics, Pepsi, Frito-Lay. I'm going to get some water here. I'll talk to everyone soon. Bye for now. Bye.